Hello. I've been trying to look for videos or information on the internet about how a cell phone works, but unfortunately, there's not that much information available. So, in order to make it easier to understand, I'm gonna try to explain it to you. So, here's a diagram. Of course, on the left-hand side, we have microphone, amplifiers, analog to digital converter, parallel to serial converter, and modulator. So these five things is what I'm gonna try to explain because if we understand this part, we'll be able to understand this part all on our own. So let's start with the microphone. Of course, as we can see, the symbol is something like this. Of course, this bar is joined to the circle. Anyways, here's the microphone. That's most probably a piezoelectric crystal. Okay, so piezoelectric crystal, it's as we know, it's a crystal with silver electrodes on the side. We have the positive terminal, the negative terminal. So if um if pressure is applied to this crystal, it's gonna induce voltages on either sides, and we can use this voltage as a measurement of the loudness or the frequency of the sound. So it's gonna be an AC, uh, an alternating current. So the waveform is going to be something like this. Here we have the voltage. Here we have the time. Okay, so amplitude will give the loudness of our voice, and time will give the frequency. Next, we have the amplifier. Okay, it's an amplifier, which is gonna be most probably gonna be an op amp, as we've studied the A levels. So what this is gonna do is we have this waveform. Suppose we have the same dimensions. We have the time, of course, the voltage. What it's going to do is it's going to amplify. What it's going to do is it's going to amplify the voltage signal or the electric signal that we have produced using our voice. So it's going to increase the amplitude of it like this. So of course, let's extend this axis. So here we have if these both graphs have the same dimensions, then the amplitude of our amplified waveform has been greatly increased. So next we come to the parallel to serial converter. That's just a box. Wait a minute. We come to the ADC. Okay, what do we do in the ADC? We have this analog waveform. This is analog. So in ADC, what it's going to do is it's going to sample this analog signal into a digital signal. So what it's going to do is um, the first thing that we need to know about ADC is that it's assigned a number of bits. Like it could be 8 bits, 16 bits, 24, and so on, like multiples of 8. So if it's 8 bits, what if if it's 8 bits, then we know that it's going to have 8 binary digits. For example, 0, 0, 0, 0, 0, 0, 0, 0. So we have 8 binary digits. And in binary digits, in binary number or the system, we know that each digit can be assigned a value of 1 or 0. So if we try to find out the number of possible configurations all these 8 bits can have, we need to use this formula. 8 raised to the power number of bits is equal to 2 raised to the power of 8. So let's use a calculator. It's going to be 2 raised to the power of 8. 256. So we can have, with the use of 8 bits, we can have 8 different levels of this analog signal. For example, so okay, let's just go into detail into analog to digital conversion. Here is our analog signal, voltage, time. So if we sample it, it's going to be turned into steps, something like this. Of course, not very accurate. It's just a rough representation. Time, voltage. Of course, you can see that's not. Of course, if we're defining an analog signal, it can have any value continuous between this range. For example, if it's 3 volts, as we took it before, -3, it can assume or it can take any value between these 3 limits. But in a digital signal, which is going to look something like this, it can have different. It can only have assigned values, so it cannot have any value between these horizontal steps. For example, the place here, it cannot have variable value between this step and this step. So if any value is found to be between these 2 steps, we are gonna let's just say I forgot the word. So if we have these 2 steps, if any value is found between these 2 steps, it's gonna assume the lower step. So let's just say if this is 0.5 and 0.6, and we have the value 0.5, 0.54, 0.53, 0.59, it's going to take the lower value, which is going to be 0.5. So that's the digital signal. The vertical bars show us the times at which the sampling has taken place. So if we find out the time period between each, this is the time, T1 is the time when first sampling took place, T2 is the second, T3 is third, so on and so forth. Okay, so there you have it. And one more important thing, as we were talking about 8 bits, 2 raised to the power of 256, and we said it can have 256 levels. That means that if the maximum analog voltage is 3 volts, then each small step of digital signal can have the minimum value that the voltage step can have in the digital signal is 3 divided by 250, which is going to be, let's see, 256 is equal to, wait a minute, 0.011 volts. 0.011 volts. Okay, so here we have 0 to 3. Analog signal can take any value between these limits, but in digital it can only have assigned values, and maximum, of course, you can have is 3, but between 0 and 3 it has been divided into 256 different levels, so the signal can assume 256 different voltages. Of course, if we're talking about if we want the digital signal to be as close to the analog signal so that the reproduction is original and very accurate, then we can increase the number of bits. For example, if we have 2 raised to the power of 16, 2 raised to the power of 16 is around 66,000. So if we're using 16-bit conversion, if we're using 16-bit conversion, wait a minute. And if we were using a 16-bit conversion, we have 66,000 possible combinations of zeros. So there are going to be 16 zeros or 16 binary digits, and we can have 66,000 different combinations. And between 0 and 3, we're going to have 66,000 different steps or the levels that our digital signal can assume. So that's that. Of course, we've only gone to ADC. Now we need to go to P2S converter. What that's going to do is, if this is the input to the ADC, so ADC samples, emits data, or transmits, that's going to be more appropriate word, transmits data as bits. So if it's 8-bit, if the conversion is taking place in 8-bit, then we can have 8 different channels. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. So 8 bits. So if we have, of course, this waveform. Of course, I'm just trying to rush through it. Okay, so let's just assume that we have the value 1 volt. Wait. Let's just say it's going to be 3 volts, the maximum. And the maximum value is going to have 8 bits, so 1, 1, 1, 1, 1, 1, 1, 1. So ADC produces the bit. This takes place as t, let's just say tx, at x seconds. So at x seconds, the ADC is going to sample the signal. It's going to produce this binary number. So ADC is going to have, it's going to produce number 1, 1, 1, 1, 1, 1, 1, 1. What it's going to do is it's going to transmit each bit on one single cable. 1, 1, 1, 1, 1, 1. So 8 bits, it's going to have 8 different channels to transmit the data. So each channel is going to carry 1 bit of the data. So 1, 1, 1, 1. So we have 8 bits. Next we have the parallel to serial converter, P to S converter. So the input is in the form of simultaneous bits. So ADC produces an 8-bit number that's being transmitted along the channels, and the parallel serial converter is receiving the data in the same form: 1, 1, 1, 1, 1, 1. Wait, of course it's going to be bits. Let's just not worry about that. What this is going to do is it's receiving data simultaneously in this form: 1, 1, 1, 1, 1, 1. So what it's going to do is it's going to transmit the data serially. So it's going to take each bit, it can take it from the top or the bottom, and transmit as this, as in a single line. So in parallel, it's receiving data from 8 different channels, and it's giving an output of single channel, but the single channel carries the whole data instead. So there are certain advantages to this, that in here we need 8 wires for transmission of data. So if we did not have the parallel to serial converter, we would be needing 8 wires to go to the modulator. But in parallel to serial converter, it's converting the data from 8 wires into just 1 wire and taking it to the modulator. What it does is that since it's just using 1 wire, it reduces the costs, and it makes manufacturing more easy. But there's one disadvantage, which is just extra information. Because it is transmitting large amounts of data, it's just one channel, it is slower compared to this, the parallel transmission. In parallel, we have 8 channels. Each channel is carrying 1 bit, so it transmits the data very quickly. But we have a problem here. It's just one channel and a lot of data in just one channel, so it slows down. So finally, we have the modulator, which is obviously which we know, what it's going to do is um, modulate the signal. We have a very let's just go back. Yeah, here. So we produce a signal, which is obviously going to be in a digital form. So this is a carrier wave, and with the modulation, we're going to get the modulated wave, and that is going to be amplified by the radio frequency, meaning that frequency is going to be increased by a large amount, by a very large factor. The switch, which switches between radio frequencies, and it transmits data. So I hope you found it helpful to a certain extent. Of course, obviously, I don't have a tripod, so my phone is not stable. But I just hope that you understand a simple part of how a phone works. One thing that we do need to talk about is the tuning circuit. It is, wait, let it focus. What's happening? It's not focusing. Okay, why not? Anyways, we have a tuning circuit. What it does is that it selects a frequency because the computers at the cellular exchange assigns the phone a single frequency. So if we're talking about radio frequencies, let's just assume that it's gonna have it's assumed it's assigned the cell phone a reception frequency. Let me just draw this on a diagram. We have the hexagon, a cell. We have the base station, which is connected to the cellular exchange. Okay, cellular exchange. We have computers here, PCs. Of course, they're going to be powerful because they're handling large amounts of data. So base station, we have this tower, which is connected to cell phones. We have multiple cell phones. Base station, we have this tower, 3 different cell phones. We have the PC. So in order to avoid the cell phone from receiving the data that it's not supposed to receive, for example, if my friend is calling me, and in order to avoid someone else receiving the call, what the PC does is it's gonna allocate different frequencies to each cell phone. So it's gonna work at 15,000 hertz. This is gonna work at 20,000 hertz. Of course, we also need to keep in mind the bandwidth of each phone. So let's just say it's gonna be from 10,000 to 15,000 hertz, 15,000 hertz to 20,000, 20,000 to 25,000. So the bandwidth is 5,000 hertz. So each phone is allocated. We need to assume that all 3 of these cell phones are in the base station. So 3 different bandwidths allocated to 3 different cell phones. In a cell phone, we have a tuning circuit. What it does is that it tunes the signal so that it only picks up the frequency that it's allowed by the PC to pick up. So, of course, because they're in the same base station, they'll be receiving their aerial. Of course, we have these aerials. Let's just assume that they were old phones. They have these aerials. They're catching up. They're catching all these frequencies. But what the tuning circuit does is that it selects the frequency that is allowed to pick up by the PC. So of course, next, there's nothing very. If we continue the circuit on the right-hand side, it's the same. It's just that all the things that happen here are opposite now. Radio frequency amplifier. We increased we modulated it, so we have a demodulator. which converts the radio frequency signal into a signal which can be handled by the series to parallel converter. Series to parallel, we know that, uh, of course, now it's going to go in the opposite direction. We are receiving data in this form. It's going to convert it, S series to parallel. Then it's going to send the data in form of, in a number of different channels. Series to parallel, digital to analog converter. It's taking that digital data and it'll turn into a waveform. So in the waveform, audio frequency amplifier, it amplifies the signal so that we can hear it through the loudspeaker, and I think that's it. Bruh.